Hello everyone. In this lecture on Z transform, we are going to define Z transform and going to solve examples on Z transform. Means we are going to obtain Z transform of the finite sequences. So let's go to define Z transform first. Let us see the definition of Z transform. Z transform of the sequence f of n is denoted and defined as Z of sequence f of n. This Z is the Z transform operator. So Z of f of n is equal to, it is the summation runs over n from minus infinity to infinity f of n. It is the general term of the sequence f of n into Z raised to minus n, where this Z is the complex number x plus iy or r e raised to I theta. So Z is basically it is a complex number. When this series converges absolutely, converges means when summation of this series is finite, then we will say it is convergent. And absolutely means when we take modulus of this term f of n z raised to minus n, and then if this series is convergent, then it will be called as absolutely convergent. So if this series is absolutely convergent, then we can say Z transform will exist. Okay, so that thing only we mention in the note. So note first, the Z transform of f of n, Z of f of n, it is also denoted as f of z, where this z is complex number. Second, Z transform exists if series on RHS converges absolutely. Third, Z is a Z transform operator. We define now inverse Z transform. Inverse Z transform, it is the operation of obtaining sequence f of n from Z transform. It is defined as Z inverse of f of z is equal to sequence f of n. This Z inverse is the inverse Z transform operator f of z. It is the Z transform of the sequence f of n. So if we operate Z inverse on f of z, it will give just the original sequence. So that is the inverse Z transform. Next is region of convergence. Region of convergence of f of z, that is Z transform, is the region in the Z plane where that infinite series converges absolutely. Okay, so region where infinite series converges absolutely is the region of convergence. Consider for f of z equal to summation from n equal to 0 to infinity f of n z raised to minus n. So this is the z transform for n non-negative. Then for this z transform, the region of convergence, possible region of convergence is mod z greater than a. So this is the region outside of the circle z equal to a, like this. So see, this dark blue color circle is z equal to a, and this dotted one, it is the region mod z greater than a. So this is the region of convergence is the region outside of the circle z equal to a. Next, second, for f of z equal to summation n equal to minus infinity to 0 f of n z raised to minus n, that is for negative n, region of convergence is mod z less than a. That is, it is the region inside the circle z equal to a. So this one is the circle z equal to a, and this region of convergence, it is inside the circle z is equal to a. Third, for f of z is equal to summation n equal to minus infinity to infinity f of n z raised to minus n, region of convergence is the annulus, that is a less than mod z less than b. So it is the region which lies inside these two concentric circles. So mod z greater than a and mod z less than b. So mod z greater than a is the region outside the circle z equal to a, and mod z less than b is the region inside the circle z equal to b. So that will give us the region like this. So this inside circle is the circle z equal to a, and this outside circle is the circle z equal to b. So region inside the circle z equal to b and outside the circle z equal to a. So the common region is the region between these two concentric circle, and which is known as annulus. So for such Z transform, this one is the expected region of convergence. In the examples, now we are going to obtain Z transform of some finite sequences. So consider the first example. Find f of z for the sequence f of n equal to whose elements are 1, 2, minus 1, 0, 1, 2, and arrow is given below the element minus 1. So this gives us in the solution, we can write f of n like this. Therefore, from we start with the minus 1 element, we know that as arrow is below the minus 1, so this implies that minus 1 is the 0th element in the sequence f of n, and therefore we can easily identify position of the remaining elements. Therefore the sequence f of n elements are like this. So 1 is the f of minus 2, 2 is the element f of minus 1, this minus 1 is the element f of 0, 0 is f of 1, this one is f of 2, and 2 is f of 3. So in this way we have identified position of these given elements in the sequence f of n. Now we will consider the definition of the Z transform. So Z transform of the sequence f of n is equal to, as this is the finite sequence, so we'll consider the finite sum where n runs from minus 2 to 3, f of n z raised to minus n. Now put the values of n from minus 2 to 3 one by one, that will give us f of z is equal to f of minus 2 into z minus into minus 2, that is z square, plus f of minus 1 into z raised to minus into minus 1, that is z raised to 1, plus f of 0 z raised to 0, plus f of 1 z raised to minus 1, plus f of 2 z raised to minus 2, plus f of 3 z raised to minus 3. So we have considered all possible values of n from minus 2 to 3 integer values of n. To get the Z transform, replace the values of f of minus 2, f of minus 1, f of 0, f of 1, f of 2, and f of 3. So that will give us f of z is equal to 1 into z square plus 2 into z raised to 1 minus 1 into z raised to 0 plus 0 into z raised to minus 1 plus 1 into z raised to minus 2 plus 2 into z raised to minus 3. Simplify the expression. The required z transform will be z square plus 2z minus 1 plus z raised to minus 2 plus 2 plus 2 into z raised to minus 3. So see, in this way we can obtain Z transform for the finite sequence. So this is basically a function of Z, isn't it? So with which we can deal easily. Now consider the next example. Second example is find Z transform for the sequence f of n is equal to 1 upon 2 raised to n. So here sequence is defined in terms of its position, that is n, and we want to obtain Z transform for it where n belongs to set of integers. Solution. So given sequence is f of n is equal to, if we put the values of n one by one, then the sequence will be like this. For n equal to 0, we will be getting the 0th element as 1. So that will give us f of n is equal to f of minus 2, that is f of minus 2 is 1 upon 2 raised to minus 2, f of 1 is 1 upon 2 raised to minus 1, f of 0 is 1, f of 1 is 1 by 2, f of 2 is 1 upon 2 square, and so on. Again we will use the definition of Z transform. Now here our n takes the values from minus infinity to infinity. Therefore the definition will be Z transform of the sequence f of n is equal to summation from n equal to minus infinity to infinity f of n z raised to minus n. Now put the values of n one by one in this expression f of n into z raised to minus n. That will give us f of z is equal to dot 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 plus. So here we have replaced the n by minus 2. Therefore we got the term f of minus 2 into z square plus. Now we replace n by minus 1. So f of minus 1 into z raised to 1, because minus into minus 1, that is 1, plus f of 0 into z raised to 0 plus f of 1 into z raised to minus 1 plus f of 2 into z raised to minus 2 plus so on. So in this way we have replaced uh, n by all its values from minus infinity to infinity. Now whatever the sequence we have been given, from that replace the values of f of minus 2, f of minus 1, f of 0, f of 1, f of 2 and so on. So that will give us the expression dot 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 plus 2 square into z square plus 2 into z raised to 1 plus 1 into z raised to 0 plus 1 upon 2 into z raised to minus 1 plus 1 upon 2 square into z raised to minus 2 plus so on. Simplify the expression. That will give us z transform for the given sequence as like this. So f of z equal to dot 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 plus 2 square z square plus 2 into z plus 1 plus 1 upon 2 z plus 1 upon 2 square z square plus so on. So in this way we can obtain z transform for the finite sequence and the infinite sequence as well. I hope you understood this. Thanks for watching this video.